Can you hear me? Hello.
Yes, sir.
Can you see the screen?
Yes,
Can
sir.
you see the screen?
Yes, sir.
Okay, let me start. Well, let me start. Okay, so yesterday I did what? Result do every second countable space is Lindelof, and for a metric space, the following are equivalent. So let me first prove that this one, every second countable space is Lindelof. Its proof is actually simple, but while writing you have to be careful. So that theorem is this. Every second countable space is Lindelof. Lindelof definition, that means you'll have to show that every open cover of X has a countable subcover. Now that means, look here, you have the word countable. So how to link with that? Okay, right? So I'm copying the proof from Willard, but I'm explaining how to write it. So that the proof, so let be a countable base for X star. Okay. Now every open cover, to take a cover here. So take a cover, open cover of X. Okay. Now look how I'm doing it. Take any U belongs to U. And then you take X belongs to U point. Now look, since this is a base, so depending on U and depending on X, you will get a member. That is, he is calling BXU. So there, by the definition of base, there exists BXU in B. such that I have this. Okay. This will depend on you, this will do this Px. Okay. Now take this collection. Okay. This collection is called B prime. Let call it B prime. What is B prime? B prime is this. U belongs to P, X belongs to U. Okay, right? B prime. Like this. Now look, Px2 actually a member of B. So this is a subset of P. Since B is countable, so this is countable. Okay, right? So that there exists an enumeration. Since B prime is countable, since B prime is countable, there exists an enumeration. Enumeration of B prime. So that means it is, but point is that I have everything like this. So that means enumeration will be something like here, countable. So enumeration of B will be like this. P x1 1 P xn un like this. Okay, because members will look like that. So I am taking account of enumeration. So it will look like this. Okay. Now look at this. Recall that this U came from here. Okay. So that U prime is a subfamily of U. And this is countable. The claim this covers. U prime covers X. So it will be done. Okay, how to do that? Be careful. So that take any X belongs to you. Okay, then how to show that? The last thing that Willard didn't say that. It is just it's a countable subcover. Okay, take again. Look, X belongs to X. Okay, so that since U is a cover, there exists U belongs to U. Take X belongs to X. All I need to show that X is the union of this. Okay, so there exists U belongs to U such that X belongs to U. Okay, so that X belongs to U, and by the way, I have look here I have chosen. Got it. U belongs to X belongs to there exists BXU. So that by this so there exists BXU such that X belongs to BXU subset of U. Got it? Okay, but BXU is one of them. Enumeration B prime. Look, B prime was actually this BXU. That is countable. So that BXU is one of them. So let BXU equal to some BXM UN. Okay, right? Now look. So X belongs to BXM. This is the last line what Wheeler didn't write. I'm writing BXM. But BXUM by definition, you see that here. U, it is contained in U. Okay. So This is contained in UM. Now look here. So X contained in UM here. So that this covers X. This argument you will have to write. That we didn't give. So that every second countable space is Lindelof. Okay. So other project I will give later on. Let me talk about that one. I'm not sure how many of you could do it. Okay. So where it is. Yes, question number 2 in the minor. Still not many of you are attending the classes. I am telling you half the class will fail. And I do not have any problem with that because this is my last semester in IIT. Okay. So that be careful. So then you'll have to repeat the course next year. Okay. So now look, level of my major exam will be same as the minor exam, not less. It may be higher, not lower. Now look, question number 2, I said if we have second countable T1 space, since it is talking about second countable, that's why I'm coming here. Second countable T1 space, then I didn't ask about cardinality, but actually it says, I said given one-to-one function. Okay, I said given one-to-one function injection. Now look, it actually says since one-to-one, so if you have it, that means cardinality of x will be same as cardinality of fx. But fx is a subset of this, so it will be cardinality of Pn. But that is the cardinality of the real line, which is small c. The result is that for a second countable space, cardinality of x has to be less than or equal to c. And if it is not T1, then it need not be true, because let me give you the proof of that. First, you take trivial topology. And this is not T1. If you have to take cardinality of x, it is huge, so is that greater than c. You can choose a c. I gave you the Cantor's theorem last time that if you take the power set of this, its cardinality will be strictly greater than cardinality of r, so it will be c. So you can always have a set like this. And this is second countable because here you have basically only one non-empty open set x, and x itself will be a base. So this is not true for trivial topology. Okay, so T1 you need it. Okay, now look, how will you give a base? Okay, this is a function. Well, look, since second countable, you have a countable base. Countable base. So here you take given x, you take it, you'll have to give a set S. Sx. Sx is should be a subset of Pn, it is going. That means it has to be a set of this. So Pn is the collection of all subsets of n. So that you'll have to identify x with a subset of n. Now look how I am giving it. Define Sx equal to n belongs to n such that x belongs to Pn. Those n. It is base, so x will belong to some Bn. In fact, it is non-empty, but even it is empty doesn't matter actually, but it will be non-empty. Okay, Sx. This is the function. Now look, I'll have to check that Ax not equal to y implies Sx not equal to Sy. This is the thing. Not all you'll have to prove. Okay, if Sx x not equal to y, now look, implies x minus y is a no, since it is T1, that's you are using. Every point is closed. So this is open. So this contains this. So there exists Bn, because this is a base. There exists Bn such that x belongs to Bn subset of x minus y. Now look, x belongs to Bn, so n belongs to Sx. Now look, Bn cannot be Nathan, n doesn't belong to Sy. Reason is very simple, because Bn, first of all, n belongs to Sy implies, if n belongs to Sy, implies y belongs to Bn. But y doesn't belong to Bn. Y doesn't belong to Bn from here. So that, since you can write this way. Y doesn't belong to Bn implies n doesn't belong to Sy. So at least you get a difference here. That n belongs to Sx, n doesn't belong to. As sets, they are not equal. So that is the function you need. Got it? Okay. So if you can give this up to this function, you'll get 4. If you can think of the function. And rest of the proof 4, 8. I think how much? 10 or 9 or 7. So this is 3, sorry. This is 3. And 2 for this, the counter example, if it is not T1. Okay, right? So that's how you use second countable. The use of second countable is not difficult. Okay, right? Okay, fine. So I need to give the proof of that. Okay, I'm just giving you the hints that how will you generate this thing. That what I'm saying, that this basically result you need every Lindelof metric space is second countable. Because by the result I already proved, other way the second countable space is always Lindelof. So it doesn't matter whether it is metric or not. This is second countable. Only thing you have Lindelof and metric. You'll have to find out a basis that how you do that. Okay, you find it in almost in every topology book, but I am not writing the details. I am just telling you the how to do that. Okay, so that let me see that how what is written. Yes. Well, first you look at Lindelof this thing. For pick up n and keep it fixed, and then keep it fixed for the time. Okay, now look at this thing, balls. Willard has used u to u. Px 1 by n, x belongs to x. Okay. So this is an open cover of x. So you are keeping n fixed. Okay. So since it is Lindelof, it will has a countable subcover. Since x tau is Lindelof, there exists a countable subcover, call it un of this. You have picked up n arbitrarily, then you're keeping it fixed. So you're not changing n now. Have covered un of this. for x. Okay. Now take u equal to this. Okay. Or b you can take that. Countable subcover in the u could find. Okay. Right. Now look, he is taking u. I am using this notation. Take union of un. Now do it for n. All these sites and that. Actually, you should understand it is not a union of sites. It's the union of the families. Okay, that means you are taking this. Okay, right? You are having all these things. Okay, but then for each u1 you have sets. Okay, so that basically you have the collection of sets like this. You have the collection of sets like this. So that let me write that. It will be not necessarily all of this come. This will be collection of sets of this form. Okay, not all of them will come. It is of this form. Now each event is countable. So it is countable union of countable sets. So this is countable. Almost everything I proved. Now you'll have to show this is a base. Or XG, metric space. So this is second count. This is the last thing. You'll have to prove it. That should not be difficult. Agreement. The way you argued for separable metric space, that way you will be manipulating with the balls. Okay. So I am leaving it to you as exercise to prove. It is just 2 lines. I could finish it. I do not want to finish it because so that at least you use your some brain. You do not. Problem is that if you do not use your brain, if people only want to mug up. Okay. So this is the proof that, but you'll have to finish it. Okay. Right. That every second countable. The Lindelof metric space is second countable. So in case of metric space, Lindelof, separability, second countability, they are all same concepts. Okay. Now let's see. I will talk about later on that countable and that. The question 1. I will put the solutions because I will send the solutions to Saurabh with distribution of marks. Saurabh will post after return the papers. So question 1. Look, this is very simple thing. I gave a first countable space. And then I gave that every convergence sequence has a unique limit. This is your hypothesis. Has a unique limit. And this is your hypothesis. So that X tau is Hausdorff. Here you look that I think this I proved. If you have only this much, then X tau is T1. But it implies this. So this is stronger. So exercise. Find a T1 space such that a convergent sequence may have than one limit. You should do it. You can ask Saurabh. But then you will be, during the exam, you'll be looking at your paper and that, like Hertzberg's. I have seen that. He was overturning pages and that to see where is what. Huh? Okay. Find the T1 space such that a convergence sequence may have more than one limit. So this is stronger. This is weaker. That's why a first countable T1 space need not be T2, so that you also find a first countable space, first countable T1 space, which is not T2. Look, cofinite topology is T1, but it is not first countables, though it is not T2, so it doesn't work. But I have given you another topology, co-compact topology. You think about on R, whether that works. So that is the whole relation in that, this thing. What is the relation in this? This plays a big role in topology, that whether a convergent sequence has a unique limit or not. Okay, right? Now, okay, so that after that, so let me prove that. Look here, the proof, should I do it? I think, or I should tell you the how you proved that every convergent net has a unique limit. How did you prove that? Every convergent net, if every convergent net has a unique limit, then X tau is Hausdorff T2. Actually, you will be using the same technique. Only thing here, the neighborhood is first countable, so we can afford to have countable base at a local base at X and Y. Okay, and then you will be using this thing. So technique is same. Technique is same. That's why I always tell you in mathematics there may be thousands of results, but there won't be thousands of techniques. Number of techniques are limited. The number of results are unlimited, sort of, you can say that. Lot. So let me, so that how will you use this technique? Okay. So I'll have to show that this is Hausdorff. Suppose not, suppose if possible actually, X tau is not T2. Okay, right? Suppose. So that means there exists a pair of points, pair of distinct points. Pair of, I know Saurabh can do all these things, but certain things, conceptual things, Saurabh won't be able to tell you. Because he will ask for the solution and he will give you the solutions. Okay, right. So there exists a pair of distinct points, distinct X and Y, such that whatever neighborhood of X and such that U intersection V is non-empty whenever U belongs to NX. My NX means an open neighborhood containing X and V belongs to NY. Okay, that will happen. Okay, got it. Now since Let a countable base at x such that it is decreasing, that I can always afford. If you don't have it, take the intersection of finitely many for all n. Make sure that you can always have. Okay. Similarly, you take Vn. Be a countable base at y. Okay. Now look, you are getting this. Have. That means un intersection Vn also will be non-empty. So that un intersection Vn is non-empty for all n. So that pick up Zn. Now the way you argued Zn belongs to un and un plus 1 is contained in un, you prove that. Take any neighborhood of x that will contain some un, and because of this, the way I picked up, Zn converges to x. And similarly, Zn belongs to Vn. Vn plus 1 contained in Vn implies Zn converges to y. We are getting a contradiction. That's it. Proof is finished. Okay, right? Got it? Okay, now come to point 3. Okay, I thought yesterday, last night, I thought I should do the paper myself to explain to you. Now, question 3. Okay. The critical point is that you have done it or not. If suppose x tau, that you should prove that if you have a set A is without an accumulation point. If A is without an accumulation point, you can argue this way: A bar equal to A union A prime. A prime is a collection of accumulation points. If you don't have any accumulation point, that means Y. So A is closed. So if you don't have an accumulation point, then A has to be closed. Okay. But it doesn't matter that, but A is closed. Of course, you can have accumulation point. But if you have without any accumulation point, then it is closed. Now, look at this topology, subspace topology, tau A. Okay. Now look, take any x belongs to A. Say x is not an accumulation point by the given condition. Let me tell you that I am giving you all sorts of open access, access to net, access to books. But the thumb rule in the US that I'm telling you, don't think so that you don't need to prepare for that. If you open your books or if you consult net source, anything more than 5 times, during the exam, you are not going to do well in the exam. You are not going to do well in the exam. You have the wrong ideas about open access exam. Open access exam, you said you don't need to just mug up. But that doesn't mean that you don't need to know how to work. It doesn't mean that you don't need to know the techniques. Okay. Accumulation, Indians are very good at mugging up. They are not very original in that thing. Okay. That's why we have this halat. If x is not accumulation of point of means what? There exists a neighborhood of x which will intersect A only in X. So there exists a neighborhood view of X such that look, Q is open in X tau. And you are getting this. That means this what? X is open in but whenever topology will be discrete if and only every singleton is open because arbitrary union of open set is open. So that tau wave is discrete topology. That's it. So if you say it doesn't have accumulation point, you get one more information that it has got discrete topology. Now look, if I have function from here, okay. This is discrete topology. So any function will be continuous. That's it. They say it. Given any function, does there exist a continuous function? So this will be continuous. But I have given that x tau is a normal space. So there will be an extension. So this is continuous because discrete topology. So there will be an extension. Since this is normal, by the definition of by Tietze's extension theorem, by Tietze's extension theorem, since this is normal, by Tietze's extension theorem, you will have this is not only topology, this kind of argument you need in analysis also. So that's it. Okay. Well, question 4, let me tell you that. This is required later on in connectedness. Question 4. Actually, I have given on a point. If you take a subset of X, non-empty you can take. Empty doesn't matter. Then empty will come X and Y. Then now look, then if you have this function, restrict to this. Since this is a one-to-one function, so this will be y minus fa. So if you call it phi, so this will be a bijection again. Since originally f was a bijection, homeomorphism, you'll have to argue that one point f is a bijection implies this. Now f is continuous, then any continuous function restricted to a subspace will be continuous. F is continuous implies now look here the other way is homeomorphism. You can take inverse of this. Now look, f inverse is this is continuous implies f inverse is continuous. So that's it. You are getting this is same as inverse of that. Look, f inverse y minus fa is actually f of this thing. So that you are getting this is a bijection. This is continuous. Its inverse is continuous. So it's a homeomorphism. That's it. All you'll have to argue that. Okay. So 1 mark here, 2 marks here, 2 marks here, 5 marks. Okay. Right? Now the next thing is, this is that I was emphasizing when I proving that every completely metroizable space, not only complete, every completely metroizable space is a Baire space. And I did last semester, I mentioned this semester, if you have complete metroizability is preserved by homeomorphism. This is a topological property. It's preserved by completeness is not a topological property, but completely metroizability. Complete metroizability is a topological property. That means it's preserved by homeomorphism. Look, I said this. There is a homeomorphism here. That basically will take tan inverse x, arc tan x. And of course, it's some translation and changing scale. You can have this homeomorphism here. You just need to mention it. You don't need to prove it. There is a homeomorphism here. Okay. So here is a homeomorphism. Composition of two homeomorphisms is homeomorphism. So this is homeomorphic to this, but this is complete. So this is completely metroizable. So this is a Baire space. That's the argument, main argument you'll have to give it. Once you have the Baire space, then by the Baire's category theorem, you have this. Okay. That one of them has to be no vertex. Okay, right? Thus there is such that is no vertex. Okay. Actually, question should be what actually? I think it should be is that N naught is not Noether tense. But anyway, whatever you argue, it is not a problem. It's not Noether tense. Okay. That actually I mean that. It should be Noether tense. But question is still not wrong. You can see that. Okay. You can think of that. I forgot to put one knot. So that by Baire's category theorem, there will be at least one N naught such that N naught is not Noether dense. Because if everybody is Noether dense, it will be first category. Okay. So I don't know how you write the answer. It is not one knot is missing. I don't know. I missed one knot. Okay. I will tell Saurabh on that. Okay. So should be not Noether dense. But what about that is a problem in that. If everybody is not Noether dense, that is possible. In fact, that is possible. Okay. Everybody is not Noether dense. That is possible. But anyway, if you write this, I will give you full marks on that. But that is also possible that everybody won't be Noether dense set. But the point is that whether everybody will be not Noether dense set. But this is the question. Every n is not Noether dense. This is possible. Let me tell you that why it is possible. I can write 2, 3. Look what I am writing. 2 minus 1 by n So 2 plus 1 by n and 3 1 minus n. That is an equal to, we're taking this. So it has non-empty interior. It is basically open. So whatever you think of its closure there into 3, it will be non-empty. So it is that. Okay. Right. Anyway, that question, this is not a wrong question, but then you'll have to argue this way, that then you don't need Bayes category theorem on that. It's a good question. Turned out that then you'll have to argue this way, that it is possible that everybody is not Novaitans. Okay. Well, I meant that not Novaitans, but actually my question become different. But that's the correct question. This way, you think about it. Okay. Now, final question that I would. Friday I will again teach you topology on that. Question 6. Okay. Look here, relation between the closed graph and this. So if f has continuous, it will have a closed graph. That is always true. F has a closed graph. F has a closed graph. Okay. Right. So that this is this. And once you have the closed graph, look here, to first countable house graph space. So basically, you can argue, you don't need to prove because it is written in the book and I gave you that you have access to book. So x cross y will be also first countable house graph. F has a closed graph. Okay. So that is, and whenever xn, if you have continuous, that is easier. Xn goes to x. If f is continuous, it means fxn goes to fx. So obviously, you take this is itself a subsequence. Okay. So xnk you take xn. Okay. So this is a subsequence converging to a point. Okay. So this is easier. This, but you'll have to prove that if f is continuous, f has a closed graph. Okay. That exactly you'll be doing this. Look how to do that. F is continuous implies f has a closed graph. So take xy belongs to gf bar. Look here, gf bar is a closure. This is in the space in x cross y. That you'll have to say. Just you'll have to mention, since x is first countable, y is first countable, so x cross y is first countable. So that any closure point can be approximated by a sequence. So this is first countable. This problem you should pay some attention because next semester you'll be doing function analysis. There is that famous closed graph theorem. So you will require this concept so that there exists a sequence xn, yn. This is for the point, this is for the sequence in GF such that xn, yn goes to xy. Look in the product topology. So you take the projections, first projections, continuous. Okay, so that this goes to this. If you take first projection, this goes to this. Projection is a continuous map, but this is coming xn. This is coming x. Similarly, if you take second projection, that will give you this. But yn is from the graph, it is coming. So that yn equal to actually fxn. So fxn goes to y. But f is given to be continuous, so fxn goes to fx. Now look, fxn goes to fx, fxn goes to y. I didn't make a mistake, I gave in Hausdorff space. So this is Hausdorff, y is Hausdorff, so y equal to fx. Okay, the y equal to fx implies xy. That is the definition of graph. Xy belongs to GF. So GF is closed. GF is closed, and here also proving that fxn goes to fx. So this is done. Okay, only now B implies A. Okay. B implies A. Now look, we'll have to show f is continuous, but since I am having first counter spaces, I can use a sequential characterization of continuity. To need to show xn goes to x implies fxn goes to fx. Or I can show directly that f is pick any point x, show that f is, use the definition, f is continuous at x. Suppose, if possible, suppose f is not continuous. Suppose f is not continuous at x. It means what? It means there exists a neighborhood v of fx. It means there exists a neighborhood, that an open set containing fx, v of fx in y, such that if u is not contained in v for all u belongs to an x. Okay? This is the meaning of the negation of the definition of the continuity at a point. Okay, so if this is not a subset, now since x tau is countable, first countable. So at x, so that you can have this countable base. This is before countable base at x, such that you can take this. This will give you the convergence. This is the idea of the metric space, and that if 1 by n, 1 by m, if m is greater than n, then bx 1 by m will be contained in bx 1 by m. That is the idea. So that now look, so particularly if un is not contained in v, that means there exists xn belongs to un such that fxn doesn't belong to v. Now look, xn belongs to un. It means because of this, xn goes to x. Now look, all the fxn's are outside v. This is your y. This is v. And all this is outside fxn. So everybody is outside that. And v is a neighborhood of, okay, right, converges. So look, xn goes to x. Okay, now how to do that? Okay, let me tell you that. It can't converge to, you can't have a subsequence of there. Look, why? Look, you'll have to find a contradiction. Now, any subsequence cannot converge. Any subsequence cannot converge. Can't converge. Suppose it converges to some point. But xn converges to x implies xn k converges to also x. Okay. What is the condition? Whenever xn goes to x, there exists a subsequence if xn k converges to this. Well, yes, graph is closed. Okay, fine. So xn k goes to x, if xn goes to y, that means xn k, if xn k goes to xy. This is coming from the graph, so that xy belongs to gf. That means implies y equal to fx, right? But look at that. What I got? If xn doesn't belong to v for all n, and y is equal to fx, and v is a neighborhood of fx. That means fx and this is not possible. Because v is a neighborhood of fx and no fxn, particularly no fxn k is in v. So this is not possible. Okay, right? So we are getting a contradiction. Okay, right? So if you assume in that graph closed, you are getting a contradiction. So that it has to be continuous at x. Okay, be careful. Read the proof of this. This is, I have given 4 plus 4. I should have given 3 plus 5 actually. B implies A. Read this proof, what I have written. Make sure that you understand. Okay. So see you on Friday. Okay. Again, I am warning to you people that if people are not attending, you should attend, and half the class will fail. I am telling you. Okay. Right? I am not making a joke on that. You think topology is an easy paper on that, easy subject on that. It is difficult. In the beginning, you need to pay attention. It is full of concepts and ideas. Once you are familiar with the concept, comfortable with the concept and ideas, then it becomes easy. Okay, see you on Friday. Bye.